Welcome to our module on deep learning. In our course, we've already encountered various types of learning. We've seen supervised learning with classification and regression, in which we learn with a labeled training set. We have seen unsupervised learning with clustering, in which our algorithm discovers patterns in unlabeled data. We've also seen in our first exploration of neural networks reinforcement learning, in which our algorithm learns to act based on a feedback and reward loop, or in our case, a feed-forward and back propagation loop. As a reminder, a neural network consists of an input layer and an output layer. The input layer contains all the input attributes for a particular tuple or the tuple's features. The output layer calculates the probability that this tuple is part of a particular class or a particular label. In between the input layer and the output layer, we find the hidden layers. Each hidden layer contains one or more neurons, and each neuron consists of a summary function and an activation function. The summary function receives as its input all the outputs from the previous layer multiplied by the weight of the connection between the previous layer and that very summary function. Each weight is individual for each output from the previous layer, and upon initialization of our neural network is assigned at random. Once the summary function has summarized all of its inputs, it passes that output into the activation function, and the activation function, which can be a sigmoid function or a tangent function like the tan function, or the ReLU function, then calculates its own output and passes that output as input into the next hidden layer, which performs exactly the same processing, and then finally into the output layer, which with its activation function most often being a softmax function, then calculates the probability of class affiliation. This is what we call a feed-forward process. We then evaluate the difference between the output, the calculated y value, and the ground truth, that is the real y value, which we know from our training data set. If there is a difference between the calculated y and the actual ground truth y, then we have to go back through our network and adjust the weights and eventually also the bias inputs in order to optimize the calculation such that finally our calculated y is very close to the actual ground truth y. This is what we call back propagation. But to understand deep learning, we have to add on to our understanding of simple neural networks an understanding of clustering. Now, clustering aims to find natural groupings in unlabeled data. This can happen through partitional clustering, in which we calculate intra and inter-cluster distances and build partitions among our data with algorithms such as k-means and k-medoids. It can happen through hierarchical clustering and our dendrograms that we build, typically with either a divisional or an agglomerative approach. And it can happen also through a density-based approach with dv-scan, which we have explored before. But on to deep learning. This brings us to deep learning. To simplify, deep learning is a combination of clustering and of neural networks that contain more than one hidden layer. It is a subset of machine learning in which networks are capable of learning from data that is unstructured and unlabeled. So deep learning combines both unsupervised and supervised learning. As we can see here, deep learning is part of representation learning, which in itself is part of machine learning. In contrast to regular neural networks, deep learning actually introduces hierarchies into multiple hidden layers. That extends to hierarchy among the layers. It also extends to hierarchies among specific neurons. This is what makes deep learning so exceptionally powerful and efficient. So deep learning is much more efficient than machine learning. In machine learning, manual pre-processing is required. That means programmers, or we, extract the features that we want to use. We normalize the input, and we have to determine whether a conclusion is correct or whether it's not correct. In deep learning, the machine will extract the features and will rank the features eventually. It will normalize where it's required, and then through the feed forward and back propagation loops, it will evaluate its own accuracy and will update the weights so that it can actually learn from itself. And at the same time, it will then select the features that have the highest value for producing the best output. So why do we need deep learning and what does it do? Because we have problems that we need to solve in the areas of images, of speech recognition, and of behavior. For that, we have a number of algorithms that are very popular. For example, our large multi-layer perceptron feed-forward neural networks. Those are the neural networks that, to an extent, we've already encountered. We have convolutional neural networks that help us with image recognition. We have generative adversarial networks that apply patterns to a whole lot of input images and from there construct new images. And we also have long short-term memory networks. But to continue with our generative adversarial, speaking of generative adversarial networks, perhaps you've seen this website, thispersondoesnotexist.com. For this website, the inventors are using generative adversarial networks in order to identify specific areas and faces, and then using specific parts of faces that have been isolated from a whole number of photographs found on the internet in order to construct new faces. So we have a pattern for a face, and then the building blocks for the pattern are being input through other photographs that are being found on the internet. I encourage you to check this out. This is really very, very interesting. And you might now think that this is very recent technology. Now, we have to understand that neural networks in computing of sorts were already discovered in the 1940s. So this is really not something that's very new. Deep learning, however, is only about 14 years old, and then our generative adversarial networks are still much younger. From there on, we have deep face, we have deep fakes, even in which we can edit videos to assume different faces. And as our understanding of these neural networks and our configuration of these various types of neural networks has evolved, our tools have also evolved, and currently we are going to take a look at TensorFlow, the latest version that is currently on the market. So why is deep learning useful? It's useful because deep learning really can learn its own features. So in natural language processing, we can use it for machine translation, we can use it for sentiment analysis, we can use it for dialogue agents that will communicate with a user in an almost human fashion. In medical usage, we can use deep learning in order to identify abnormalities in a lot of medical images. That's X-rays, ultrasounds, CTs, and MRIs. We can use it to cluster patients into risk-based cohorts and to discover relationships between symptoms and outcomes for clinical decision support. And in fact, this is where deep learning is very often used. Today, one of the most important factors for the increased success of deep learning techniques is an advancement in computing power. Graphical processing units, or GPUs, and cloud computing are crucial for applying deep learning to many problems. Cloud computing allows the clustering of computers and on-demand processing that helps to reduce the computation time by paralleling the training of the neural network. GPUs are special processors for high-performance mathematical calculations. They speed up the computation of matrices. But TPUs are tensor processing units that are highly optimized for large batches and have the highest training throughput. Typically, GPUs are more precise in their calculations, but TPUs are faster. So, how does deep learning work, technically speaking? Deep learning starts with neural networks. Here again is a summary of how neural networks work. And we can already see that there are a couple of issues that we need to manage, especially when we come to the output. Number one, we need to manage the whole idea of overfitting, because as neural networks optimize themselves, overfitting can become a real problem. And as they optimize themselves, even with a gradient step down or a gradient descent, the computational cost can become forbidding. So now let's talk about how to manage overfitting and how to deal with the computational cost. We can further reduce computational costs by leveling the computational workload when it comes to building and applying a deep learning model. This happens by number one, carefully evaluating the number of hidden layers needed, the number of neurons needed in these layers, and the complexity of the selected activation function. Number two, it also happens by selecting how many tuples of the dataset we send through the network at one time, that is, in one iteration. That is called the batch. Once a batch has been processed, the model weights are updated, but only at the end of each iteration and on the basis of the entire batch, not the individual tuple as it was with the basic neural network that we have discussed before. The batch size determines how many iterations are needed in order to process the entire dataset and how often the weights are being updated. When all tuples have been processed, we call that an epoch. Using batch size, we can fine-tune how much of our computing resources we want to allocate to each step in the process. The calculations for one epoch are in the red box here, but that is not all. We can also tune how many times we want to cycle through the entire dataset. That is, we can also set the number of epochs that we want to run. As you can tell, when we process truly big data through a truly complex deep learning model, tuning these parameters, batch size, iterations, and epochs, helps us build the most accurate model with an optimized impact on our existing computing resources. And now please take a look at this example and step through it in your mind. So now let's look at batch size and epochs in a little bit more detail. Batch size is the number of examples from the training dataset that is processed in one iteration and is used in estimating the error gradient at the end of this iteration. Batch size typically comes in three flavors. Batch gradient descent means that we're using the entire training set in one iteration. This is where one iteration equals one epoch. Here, the number of updates to the weights equals the number of epochs that we run. Stochastic gradient descent is the opposite, where our batch size is 1, meaning that we process only one tuple in each iteration and update the weights after each tuple, as shown in our previous discussions of just a simple neural network. Lastly, we have the most popular option, the mini-batch gradient descent, in which we specify a batch size that is typically a good divisor of our dataset, that is, a number by which we can comfortably divide our total number of tuples. As you can see in the gray box here, the number of epochs, that is, the total iterations through the entire dataset, is traditionally large, until we have sufficiently minimized, that is, optimized, the error in our model. You may have already guessed that we have a slightly different deep learning model for every practical purpose. And you'd be right. Here is a list of the most popular ones. We have already discussed the feed-forward neural network, which is used for your run-of-the-mill classification and regression that is based on input features. Then we have the convolutional neural networks, which are typically used for image classification or object detection. These are neural networks that use convolution, which is multiplication or another dot product in the place of our general matrix multiplication in at least one of their layers. So the input for this is a tensor with image properties like number of images, image width, image height, and image depth. And we'll discuss these in a follow-up video. Next, we have our recurrent neural networks, where connections between nodes form a directed graph along a temporal sequence. This allows the network to exhibit temporal dynamic behavior. We can use those for image classification as well as object detection and video action recognition, etc. Lastly, we have the encoder and decoder architecture in our supervised learning that allows us to perform semantic segmentation, machine translation. So we use that very often for natural language processing. Then down here, we have deep reinforcement learning, which is our artificial intelligence and uses a reward system in which a system learns our moves, for example, at game playing, in order to outsmart us down the line during future game moves. Now let's move on to our unsupervised learning. In our unsupervised learning, we have our autoencoder that is used for unsupervised embeddings, denoising, and most interestingly, though, we have here the generative adversarial networks. Those are used for the unsupervised generation of realistic images and movies. Remember, this person does not exist at www.thispersondoesnotexist.com. That's what we're talking about here. The results of these efforts are also often called deepfakes, and they exist in both images and movies. Take a look at the video of Jim Meskimen's performance of Pity the Impressionist, in which a generative adversarial network here is used to insert features of 20 different actors that we see down here into the performer's face as he speaks without any interruption. So this is what generative adversarial networks do. So to summarize, deep learning is a combination of neural networks for specific purposes. Less pre-processing is needed as deep learning networks discover and optimize their own feature space. We use batch size and number of epochs to manage the trade-off between optimization of accuracy and minimization of computational cost. Batch size is the number of tuples processed in one iteration across the network. Weights are updated at the end of each iteration. An epoch is a pass through an entire dataset and consists of one or more iterations depending on how the batch size is configured. Now, deep learning networks can be used for regular structured data classification tasks, for image classification as convolutional networks, and for unsupervised tasks, especially deepfakes, as generative adversarial networks and more. Deep learning is usually programmed in Python, often with the help of TensorFlow and its libraries. And now, let's go on to our next video in which we talk about TensorFlow.